So folks, now that we've introduced the idea of a vector valued function, let's repeat some of the work that we've done before as we look at some examples. So for example, here I'm asking you to come up with a function. Notice I'm using the word a function because it depends on the parameterization, among other things. But let's find a function that describes a line passing through these 2 points. So we saw previously that we described our lines as r is equal to some r naught plus t times some direction vector. The only difference here is we're going to think of this now as some function r of t, and it's going to be mapping from r to r2, and I shouldn't put a of t there if I'm writing in an arrow notation. And so we still are going to find an initial position, and so let's use as our position vector just the position vector p here, and so that's just the vector 1, 2, 1. And let's use as, well, we need to come up with a direction vector. Of course, for this line, we could head in either direction, but let's go from point P to point Q, so that'll be that displacement vector. And so this would be, if we're going from P to Q, this would be the vector -1, 0, 2. And so now we can go ahead and just give this function where r of t is the function, and there's many ways we could represent this, but I'll represent it this way in this case. So this would be 1 minus t, comma 2, comma 2t plus 1. So there it is. But folks, we do need to, because we want to describe this line, and we said we're doing this for all real numbers, we do need to make sure that we give the domain. So with the domain, -infinity less than t less than infinity, and there we have a function that describes that line. So we could do the same thing down here for this line segment, but the difference is now we're going to think of our function as going from, usually when we do line segments, we're going to restrict ourselves to time values between 0 and 1. Now you could do other segments, other limited time values for a line segment, depending on, you could do different parameterizations, but we're going to restrict ourselves for time values between 0 and 1. You don't have to worry about writing it this way, but instead when you give the function, which would still be the function r of t equals, and let's just represent it a different way, 1 minus t, 2, and 2t plus 1, that you make sure that you restrict time values between 0 and 1. And that's the most natural parameterization, I think, to pick, because when time is 0, we are at point P, and when time is 1, that places us at point Q. But you could certainly use other parameterizations. Okay, so now the last thing we want to talk about is the domain of a vector valued function. And if I don't explicitly state what the domain of R is, what values we're allowed to plug in for time in this instance, then we're just going to say that it's implied to be the largest set of values for which the given vector valued function is defined. So for example here, we've got our 3 component functions, and I'd like to spell those out here because we haven't done that yet. Our first component function is the function 1 over t plus 4 times t minus 4. Our second component function is the tangent of t, and our third component function is the function the natural log of t minus 2. So if we want to give the domain of this, we want the largest set of real numbers for which this vector is defined, and this vector is defined if all of its components are defined. And so we see that from the first component function, t is not allowed to be -4 or 4. So for f of t, the domain of f is all real numbers such, let's see, it's the domain of t, all real numbers such that t does not equal plus or minus 4. And for this second component function, the domain of it is the set of values t such that, whereas the tangent curve undefined, well, that's wherever we have an odd multiple of pi. T is an odd multiple of pi over 2. Odd multiple of pi over 2. And then for our third component function, we have that its domain is the set of values t such that, and now we can only take the natural log of positive numbers, so we need t to be greater than 2. So if we want the domain of R, this function R, we need to take the largest set for which all these components are defined, and so the domain of the function R here is going to be set of values t, I wrote an x, t, such that t is greater than 0, and t does not equal 4, nor an odd multiple of pi over 2. That's really awkward to write out. So another way we could do that maybe is we could just do it by way of a visualization. So we would go from 2 to, let's see here, the first odd multiple of pi over 2 that's bigger than 2 would be 3 pi over 2. So anything on this interval would work. Or from, let's see here, we could go from 3 pi over 2 to 4, or from 4 to 5 pi over 2, union with, and then we continue on, so now we just have the odd multiples of pi over 2, 5 pi over 2, to 7 pi over 2, and 7 pi over 2, to 9 pi over 2, and then we could just put dot, 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 because I think the pattern should then be apparent. So issues of domain really just boil down to looking at the domains of the component functions, and that's going to be really useful going forward. Okay, folks, at this point you should be able to complete the MyMathLab pre-work for this section. Do let me know if you have any questions, and we are going to be exploring this more in class tomorrow, as well as through the rest of this chapter. Thank you very much.